Without energy, living things, and everything else for that matter, just sits there. So far, we've talked a lot about matter, the physical stuff that the universe is made of, that we're made of. But without energy, that matter can't really do anything. Energy is a tough one to define. It's just the ability to do work. So it's a force of some kind. And it comes in a lot of different forms. And that's something that's a little tough to wrestle with. Give you a few examples and then kind of bring it down to what matters to living things. So, drawing a picture of the sun. So that gives off heat energy and light energy. So those are both different forms of energy. We have electricity, we have mechanical energy, there's atomic energy. So lots of different forms of energy are out there. But in terms of life, here's what it comes down to. The ultimate source of energy that powers life on Earth is the sun. So that's the energy input. And energy, unlike matter just cycles. It goes through these cycles. There's the carbon cycle and the nitrogen cycle. And we'll see a lot in living systems how all these materials just get recycled again and again. But energy is not like that. Energy flows through living things. I know that sounds kind of like Star Wars and the Force, but that's what happens. Energy comes into us because the sun powered a plant to make food. The plant was able to capture some of that energy chemically in here, then we can eat it, and that powers us. So there are a couple of laws, there are four of them really, but we just concern ourselves with two, that talk about how energy can move around. So the first law is simple. It just says, we're not going to make any more energy. And it doesn't go in a black hole somewhere. There's only so much energy around, but we can move it between one form and another. It's fine. We can do that. We can turn sun energy into food energy, into motion, or all kinds of other stuff. So that's the first law. We can transfer energy around wherever we want. It doesn't just fall into a black hole and we can't just generate it out of nothing. Okay, so we can move energy around. The second law is that transfer of energy from one thing to another is not perfect. Every time you transfer energy, you're going to lose some of the useful energy in a system. Now, all the energy is there, but the useful energy goes down. And that usually comes out as two possible forms. One is heat, and the second would be disorder or chaos. So as we use energy, as we make all these transfers, just in our daily life, there's a lot of junk that builds up within us, right? And heat. So the heat keeps us warm. We kind of like that. Sometimes if we use a lot more energy, then we have too much heat and need to get rid of it. But there's also all these messes made in our cells, just like in our houses, right? As we go around doing all these energy transfers, living life, a mess gets made. And we have to spend more energy to clean up that mess and keep the body in order. So that's kind of a rough sketch of the laws of thermodynamics and why they matter. Next, let's talk about chemical reactions. So even though there's a lot of different ways we can move energy around from one form to another, most of what we're going to talk about in the human body, the basis is chemical reactions. Remember, those plants did a great job for us capturing that sunlight energy and turning it into chemical energy, food. And even if another animal eats this apple and then I eat that animal, it's still coming from the sun. That's where the energy came from. And then we're going to do some chemical reactions inside of our cells to release the energy in these molecules to make it useful in the cell. Okay, that's the laws of thermodynamics again. We're going to release that energy, first law. Second law is that's going to give off some heat and we can't use all of it. So, easy illustration. Got this little lighter. And inside here, there's a chemical, right? It's got a lot of energy in it. And if I push this button, well, nothing happens. we need to get this chemical reaction started. And so I need to make that spark. And then that gas released undergoes a chemical reaction and releases energy. In this case, you can see it. A lot of the stuff that happens in our cells is not real visible. Just it gets one molecule turned into another one. And that's what happened here. We had butane, an organic molecule in here, that when it burned with the oxygen from the air, those recombined, formed carbon dioxide, water, and gave off heat energy as well as light. Okay, so there we were transferring energy around and molecules were changed in the process. It's going to be a repeated thing. We're going to see that over and over and over again. Let's take one more step and talk about this chemical reaction, specifically breaking down an organic molecule into smaller ones. And I'm going to show you that on a graph. All right, scientists love to graph things. I'm no different. So here's our graph. We're looking at the amount of energy, so low down here and high up here, over time. So we're just going to look at this same chemical reaction. We've got butane in the lighter and oxygen from the air. When we create that spark, then it's giving off carbon dioxide. That's what the butane was turned into, and water, which you can't really see, but it's there. All right, so actually you can't see either one of them. And then we saw a bunch of energy given off. On a graph, here's what that looks like. Butane and oxygen, the start of the reaction, that's what we had. And they have a lot of energy in them. So we're going to put that kind of high on the graph. All right, so there they are, nice and stable. They're just going to stay there as butane and oxygen until we start the reaction. Carbon dioxide and water, these are basically calorie-free. They have no useful energy left in them, so they're down here. But remember, I couldn't just push the button and it automatically happens, which is great because we don't want this butane in here, if it's spilled out, to just spontaneously combust and burst into flames. We want to have to start that reaction. So we actually had to put a little energy into it. So this was kind of that outside input of energy from me flicking the thing and causing a spark, which then allowed the chemical reaction to proceed. And then basically one butane molecule combusted, turned into this, gave off energy, and ignited the next one, and the next one, and the next one, and the next one. And what we saw out of that was that energy was given off. So we could call this an exergonic reaction. Energy left this chemical reaction. But this up here is the activation energy, the energy I needed to put in to get this chemical reaction to happen. Now, we don't always have to have these go downhill. Couldn't we do something a little bit different? Well, let's go back to the sun and the apple. So that was an endergonic reaction. In that case, the sunlight from here provided the energy to get us from carbon dioxide and water that the plant took in and produced the apple, which is full of sugars. So there's an endergonic reaction. It took molecules like carbon dioxide and water, did photosynthesis, required energy input. Now we have a higher energy molecule. Then we take that and we put a little bit of energy into it, break it down to carbon dioxide and water, and now that powers us. It gives off energy that we can use inside of our bodies. Just like we were able to ignite the butane, give off CO2 and water, and the energy given off in that case was heat and light. So there's a basic overview of energy, how we move it around, and the rules for how that works. Hope that helps.